In this video, we are going to be covering week 3 from ENGG 201, where we talk about binary mixtures and diagrams that represent binary mixtures. So I want to start us off just with an opening question. So if we had two different substances, we have acetone, which has a boiling point of 56.2 degrees Celsius, and ethanol, which has a boiling point that is higher at 78.5 degrees Celsius. For a mixture, what phases are present below 56.2? So to answer this question, both will remain liquid because acetone has not yet reached the point where our liquid turns to vapor, and nor has our ethanol. So then this is liquid phase for both. Now between 56.2 degrees Celsius and 78.5, we will see both liquid and vapor. So then this ethanol has just turned to vapor, and so has our acetone in between this scale. So then we'll have and finally over 78.5 degrees Celsius, then we have vapor phase, both components. Okay, so binary mixtures is basically just, it's given as a mole fraction of whichever substance you have in different concentrations, and it shows that they react to temperature as a result. So, taking a look at this example, in the two-phase region, so this kind of looks similar to our PT diagrams. Our two-phase region is identified by whatever lies in between these curves, where vapor is on the top border and liquid is at the bottom border. So we have two different compositions. So why is that? So before we answer these questions, there's a couple things you need to know about these kinds of diagrams. So let's say this, so from our previous question above, this graph is a visual representation of that information. So we're still going to have our mix of ethanol as well as our acetone. So, mole fraction of ethanol. If we have a mole fraction of 1, that means this is 100% ethanol. So this is pure ethanol. And then the other side is our pure component of the other ingredient. So this would be pure acetone. Because if there is a 0 mole fraction of ethanol, that means there's none present, which means all of our other component is present in that case. So we want to find, in the two-phase region, the vapor and liquid have two different compositions. So why is that? So this is answering part B of our previous above question. So we know that for our acetone, our boiling point hold on. Yeah, so our acetone is, let me just color match these better so it gets less confusing. So pure ethanol and pure acetone. Our acetone has a boiling point of 56.2. So we just measure from our left side of our x-axis and find where it intersects. So here is our 56.2 degrees. And then if we did the same for the right side, we'd find that it's 78.5 degrees Celsius for our ethanol. we can answer our first question. So the lower boiling point of acetone means it is converted to vapor quicker. More readily, I will say. That is our first question solved. So let's take a look at our second question. And at a 30% ethanol mixture, so if we find 0.3 on our graph, on our x-axis, that is roughly there. And we hold it at 60 degrees Celsius. So let's follow our point up to our 60 degrees Celsius. What is the mole fraction? So similar to our previous questions with our PV diagrams, if we have a point that lies within an envelope, we can read to the left and to the right and measure those two compositions. So if we drew it down, for each region, where along this curve, since it borders liquid, this is our liquid composition, and this side is our vapor composition because it borders our vapor region. We could say that our molar composition of our liquid is about, so if we read down, that's about 0.38. And then for our vapor, reading to the left, that's about 0.24. And that's how we can use our graph to find different compositions at a specific point. And this only works when we're inside that envelope because we're going to have two different compositions of liquid and vapor. Okay, last one. A mixture containing 80% mole ethanol, so let's find that on our graph, is heated from 55 degrees all the way up to 80. So we want to follow this line here. So describe what happens. So as you can see, this line intersects our liquid curve as well as our vapor curve. And we can imagine reading across. So we're going to start with our our liquid phase, sorry. As we increase temperature, it turns to vapor. So when we enter our envelope, we're going to find our first point, which is our bubble point. So this is when we find our first bubble in our system. So when we have something that's mostly liquid, when that first little piece of vapor shows up, that's what this value is here. So when we intersect our liquid boundary line, if we read across to the other part of our envelope and then read down, then we can find the composition at which our system is at our bubble point. So I'm just call this point A. So that's at point A. And then our dew point is where it intersects our second boundary region, and this is going to pure vapor from our vapor and liquid. So this means only a little drop of liquid exists. So this is called point B, and we're going to call this dew point. So right here. Okay, so that's kind of a basic analysis of how to read these graphs, just to start us out. It'll make a lot more sense once we keep going. Okay, so let's say if you had 10 kilomoles total, 80% of which is ethanol and 20% of which is acetone at 72 degrees. So let's just find our mole percent. So our total moles is 10 kilomoles. So that means for ethanol, this is 80%. So then this becomes 8 kilomoles. And then for our acetone, at 20%, this is, right, so both of these components should add up to our total, which is 10. So how much is in each phase? Okay, let's find out. So our X liquid minus X total, so we're going to find what that plot is first. So let me zoom in a little. So we are at 72 degrees. It's about here at 1 atm. And we can use our ethanol. This is equal to 0.8 mole fraction. So we've plotted where our Y is going to be, 72 degrees Celsius. And now let's find 0.8 mole fraction ethanol. So then that brings us to this point right here. So that's our first point. And read across to find our liquid and vapor compositions. So this is our X vapor and our X liquid. So X of our vapor is roughly, so if we draw down, this is about 0.67. Then our X liquid. So we take from this point and we draw down. I'd say that's about 90. So 0.9. So going by our lever rule, we can solve for our composition of, let's say if we just focused on ethanol for now, since we readily have that information available, since we are using our ethanol mole fraction to find our different compositions. So then if we did that, so in our vapor phase, we're not sure, but we know our total moles. So then this is X liquid, so that's 0.9 minus, and our total X is 0.8. And then this is our liquid, 0.9 minus our vapor, 0.67. And this times our total moles, which is 10 kilomoles. And then this becomes so it's 0.9 minus 0.8 divided by 0.9 minus 0.67 times 10. So our moles of vapor at this point for ethanol is roughly 4.348 kilomoles. And then we can use our same technique for the moles of our liquid of ethanol. Again, this will start to make more sense as we do more examples. So completely miscible liquids with an azeotrope. So this is where the composition of vapor and liquid phases are equal. So this is basically just a dip in the envelope where they experience 2 points of contact. And for both our compositions, both of our components, the compositions of liquid and vapor become the same in this region. Then we have partially miscible liquids. So this will show different diagram boundaries where we have vapor and liquid in these two envelopes. So this is our azeotrope, which we just looked at with our previous example. But now we also have a region where we have two liquids, a region where we have one liquid in green, and a region where we have the other liquid. So we are asked for degrees of freedom at point E. And if you look at E lies on the triple point line. So E is on triple point line. So what does that mean? That means we have three components. Binary system. 2 components plus 2 minus 3 phases. So this is equal to 1. Right, so that means the rest of our values are fixed, but we have one that we are able to change. So temperature and pressure are fixed, so I think we can change our volume or our mole fraction. So completely miscible has a eutectic point. So some substances solidify at a temperature that is lower than the melting point of both of our substances. So here's melting point of substance A and our melting point of substance B, right? And we see that this point here, our eutectic point, is below. So this produces a phenomenon where they are completely miscible. This word miscibility just means how well something mixes. So if something's completely miscible, they completely mix to each other. Partially, they become partly mixed, and completely immiscible means that they do not mix at all, our 2 components. Here are some other examples of these graphs. We have partially miscible solids as well as completely immiscible solids. And it makes sense that in our completely immiscible solids, we just have a boundary splitting our liquid and vapor regions, or liquid and solid regions, because they only exist in one of those 2 stages and not a combination of both. So that's why we don't have our envelope in our completely immiscible solids. Okay, so we're going to try this example here. I'll try and do a better job of explaining where things go and why. So let's start off with this example. Before we do anything, let's label some key terms. So this diagram looks an awful lot like our partially miscible solids diagram up here, where we have 2 different kinds of solid phases on either side of our borders, and we have a mixture of the 2 caused by each corresponding liquid and solid. So with that in mind, let's start labeling what we need for this. Okay. So we know that we have two regions. We have our liquid region, and then we have solid A and solid B combined in this region. In this region, which I'm going to highlight in green, we have the presence of our first solid. So this is mass fraction of B in A. So this means at this point here, we have pure solid A. So then this is pure A and pure B because we're looking at our mass fraction of B in A. So then this is pure B because a 1.0 mole fraction means that it's only just that one component present, which is our B. In that same regard, we don't have, so compared to our graph that we looked at, we actually don't have a solid region for our second component, but we can still make some inferences. So because this region is bordering our liquid phase and our solid A phase, this is liquid plus solid A in the section here. And since this section borders our remaining solid B, this is solid B plus our liquid. Okay, some key terms. This line here, bordering our envelope region of combined phases and our pure liquid, this is called the liquidus line, where the mixture borders being a liquid. And we also have where the solid borders our envelope region. So pure solids, this is called solidus line. And finally, we have this line here, which should look familiar, borders all three different components, all two different components and our two phases, and this is called our triple point line. That's part A. Label all the regions on the phase diagram. And part B is specify the melting points of pure A and pure B. So we already established that our pure A is on the left side and pure B is on the right side. So just find where it intersects our temperature axis. So this is, let's see if I can clean this up a bit so you can read it better. So that's about 106 equals about 106 degrees Celsius. And then for our B component, we want to find where it interacts with our temperature axis. So that would be this region here. And that's about, let's just round up to here, that's about 100. So at pure B is about 100 degrees Celsius. So we want to find the maximum solubility of I, so that's A in B, and then we have B in A. So for this question, we want to imagine that we have pure B, and we're mixing in A. So we start from this side, and we can see that at this point here, so I'll draw that so you can see it, we have all of our B in A. So that means at this point, if all of our B is in A, if all of our A is in B here, hold on hold on. So if we want to maximize solubility, that means we'd have the most B we can, which is 1.0 in our mole fraction. And we want to have the least amount of A, and that would just be 0 in this case. So then this is 0% for A and B. Now if we wanted to do the same thing here, we want to find where our A borders our B, and that would be at this intersection right here, right? Because it's bordering B in this region here. So if we read down, that is about 0.26 for B. And then if we take that as a percentage, this is 26%. Okay. So for part D, starting from a temperature of 110 degrees Celsius, so I'm going to do this in fuchsia. At what temperature will a solid phase first appear in each of the following mixtures? So 30% mass B and 30% mass A. So let's start with our first one. So at a temperature of 110, so that's all the way at the tippy top. And what temperature will a solid phase first appear for the following mixtures? So then if we were to plot 0.3 and go up to our 110 degrees, that would bring us here. So we want to cool, so which means we're going to decrease temperature, so we're going to travel downwards along our same molar composition, molar ratio. And we want to hit until we get our first appearance of solid. And because of this envelope here, because it has both liquid and solid present, we would measure where this point intersects with our y-axis when we read across. And that's about 97. About 97 degrees. Okay. And for part 2, we want to find 30% mass A. So if we have 30% mass A, that means we have 70% mass B. So let's start at our 70%, also at 110. So let's start from there. And then we read down in a straight line to cool it until we hit our liquidus line again, which borders our solid B and liquid composition. And if we read across, this is about, let's see, let's say that's about 86 degrees. Okay, only a couple more left to go. So part E, what is the composition of each of the solid phases in part D above? So because part E draws from what we did with part D, let's use the same color. So for our first one, so this is with respect to B. So when we read downwards and we read across to our boundary with our solid A line, this gives, so composition, so X of B is for solid, so this is N B solid, and that is equal to, so we read down, that's about 0.0 1. That means for our A, this gives, so in our solid, 0.9. So the two of them add up to be 1. And since we're already given the solid formation, so then if we have, sorry, for the liquid, my bad, this is 0.3, which we're given, and then for A, so 1 minus 0.3, that's 0.7. So for our final portion of part F, let's first find the point that we're given. So 60% mass B at a temperature of 82. And when read, that brings us to our eutectic point. So basically our process is the same that we did for part E. We're going to read to each ends of our bounds, and then we're going to read down. So at the end, our B of our solid is equal to 100%, and for our solid A, this is equal to 0.25%. Okay, so that's all we do for question F of this example. I hope this is starting to clear up a couple more things. In the next video, we will be going through some practice that relates more to these binary systems, and we will further decode different applications of how to use them. I'll see you in the next video.